Now the idea of kernel methods extends well beyond the quadratic transformation example that we saw on the previous slide. It can be extended to, in fact, any arbitrary polynomials. A polynomial kernel takes two data points, x and x prime, and computes 1 plus x transpose x prime raised to q, the qth order polynomial kernel, where q is any integer that is greater than or equal to 2. This will compute an inner product for qth order polynomial transformations. So if q was a large number, like let's say q is 20, then the simple method, the original method, would be to first take x and x prime and transform it into polynomials, like into z and z prime, that are of degree 20. So they will have a very large number of terms in them, as we saw in a homework example before. And then compute the inner products between z and z prime. That will require a significant amount of computation. But this kernel trick basically allows us to just compute the inner product between x and x prime, which is very easy. So in the case when x and x prime are two-dimensional, you just have to compute like inner product between vectors of length 2 and then raise it to the power of q. So this will significantly simplify the amount of computation that needs to be done to compute the inner products. However, the most sort of popular kernel method that is used is to use radial basis functions. In radial basis function, the kernel that we use is the exponential function. It's the exponential of minus gamma times the norm of x and x prime square. So here gamma is known as the kernel width. It's typically a constant. And it turns out in this case, the Z space is essentially infinite dimensional. So if we take a simple case, if we take the case of linear function, of when the case when x is linear is one dimensional, so d is 1, so x is now a scalar. The kernel function here will be e to the minus gamma of x minus x prime square. Let's for simplicity assume gamma is 1. So this is e to the minus x prime square. So if we were to expand this, what do we get? We get e to the minus x square plus x prime square plus 2x x prime. So I can write this as e to the minus x square, e to the minus x prime square, e to the minus 2x x prime. So if I write it further, then this exponential, or actually this is a minus here, so this becomes a plus. This is, if we do the Taylor series expansion, this is 2 to the k, x to the k, x prime to the k over k factorial. Okay. Now what we can do is we can write this as an inner product between z and z prime, where z is a vector like this, e to the minus x square times 1 square root of 2 over square root of 1 factorial times x, square root of 2 square over square root of 2 factorial times x square root of 2 cube divided by square root of 3 factorial times x cube, and so on. And z prime is the vector e to the minus x prime square 1 square root of 2 times x prime divided by square root of 1 factorial. Second term is this. Third term is going to be this, and so on. You can see when you take the inner product, you have e to the minus x square times e to the minus x prime square throughout, which accounts for these two terms. Then if you expand the summation, the first term is a 1. When you take the inner product, multiply the components here, you get a 1. If you look at the second term, it's 2x x prime over 1 factorial when k is 1. So when you multiply these two, you get 2 x prime divided by 1 factorial. Take k to be 2 and you multiply these two, you get 2 square over 2 factorial x square times x prime square, and so on. And then you sum up all the terms. So now what we have is, if you had to directly compute z and z prime, they are both infinite dimensional vectors. So if you had to first compute them and then compute their inner product, it would take forever because these are infinite dimensional vectors. However, if you applied the kernel trick and directly computed this function, you can compute the inner product essentially in a very essentially in one computation. Just compute the difference, square it, and exponentiate it. So the kernel trick can drastically reduce the amount of computation that is needed in computing the inner product. So what we can do is, we can now note that the dual formulation which is n going from 1 to n, alpha n ym alpha m times zn transpose zm, this only depends on Zn and Zm through Zn transpose Zm, which is now the kernel function, which can be computed easily using the kernel function. So all we have to do is take this quantity and stick in here. The remaining constraints don't even depend on the z and x vectors. So the entire dual formulation can be solved easily with the same complexity as was needed to solve when we did not do the nonlinear transformation. So this can be solved easily using the kernel function. Also, if you look at W now, W will be summation over alpha n, y, and zn, where Zn is a support vector. So our decision rule will be the sign of summation, or we can also write this equivalently, because if Zn is a support vector, it's equivalent to saying that alpha n is positive. So alpha n's are solved here in the dual solution. We get sign of alpha n, yn, W transpose X plus B, right? Because actually, I did it too fast. Let me do it one step at a time. Sorry about this. Y hat is sign of W transpose X plus B. Now, if I were to substitute W, I will get the summation of alpha n is positive, alpha n yn, okay, I think I'm doing things too fast here. This should be a z because we are in the dual space. Zn transpose z plus b. This we can again replace by the kernel between xn and x. So in the transformation space, when we were to do the nonlinear transformation, our decision rule will be this. We will compute z to be the nonlinear transformation of x, the data vector that we are interested in. Compute w transpose z plus b. But because w is written in this form as a linear combination of the support vectors, when we substitute it in here, again our decision function will only depend on the kernel between xn and x. We can use the kernel function to compute this. And B2 can be obtained using just the inner product. So we saw this before. We can write B in the form. So the point is, we never have to actually go to the Z space in order to implement our nonlinear transformation. As long as we can compute the kernel functions easily, that is all that matters, and they can be used to compute the inner product, and the dual formulation can be solved rather efficiently. So if we can have a very complicated nonlinear transformations, and maybe we can get a very sophisticated looking decision boundary. Perhaps this could be the decision boundary we have after we apply some nonlinear transformation. We might get these 2 points, maybe could be the support vectors of our decision boundary. And all this computation can be done very efficiently using kernel methods. So if we had to compute a complex decision boundary, we will apply a nonlinear transformation, and the kernel method will allow us to do this computation rather easily. So this ends our discussion of support vector machines. Starting next lecture, we will go to a new topic called pack learning and theory of generalization. Once we understand this, we can actually go back and see why such kernel methods are not only a computationally efficient method, but the decision boundaries that we get like this from this SVM will in fact have good properties, will be a good solution in that it will perform well on unseen data and give us smaller test error. At this point, we cannot say that this solution will in fact perform well on unseen data. Perhaps going to such high dimensions in the nonlinear transformation is an overkill because we may not be able to have good generalization. But it turns out this is not the case. It is in fact such methods will generalize well on unseen data. So kernel methods plus SVM are a very popular tool used in many machine learning algorithms, and they generalize well. But to prove good generalization properties, we have to understand some theory of generalization. So starting next lecture, we will move on to this particular topic. Thank you.